So you're working with a marketing mix model. What happens when you add a second media channel that is highly correlated with the first media channel? So you're going to introduce strong multicollinearity into the model. How is the marketing mix model going to be able to handle that? So what I really like to do here is generate data. So we know the exact relationships that are going on. We know exactly what the ROAS of each marketing channel is, and we can see how well the marketing mix model picks it up. Let's take a look. So the first thing we're going to do is start with a model with one media input. So I'm going to enter a whole bunch of parameters that we're going to see later. These are going to be parameters that are going to be part of the marketing mix model. We define common functions, the add stock and the hill function, and we're going to calculate a ROAS. So we're going to generate some data. This is going to be our one media mix model. This is going to have T time periods and geos. So it is a geo-based hierarchical media mix model. So you can imagine if this could be many countries that have panel data stacked on top of each other, or it could be many DMAs or like cities in the United States that all have data getting trained at once. But importantly, we set all the parameters, we add a whole bunch of random noise, we have a control variable in there, and then we have our media mix model, which is highly correlated with our control, and we generate the data after doing the transformations. Here is just our output. It's a function of a baseline, beta times the transformed media inputs, plus the control, and then some noise. And we can see we can calculate what the true ROAS is just based on the data that we generated. And in this case, it is 1.21. So for every dollar of media investment, you're getting $1.20 back, or about a 20% ROI. Now, if we take that saved data and I bring it into RStudio, because a lot of these packages just are much better in R. Now, I probably could have generated the data in R. I'm just comfortable in Python. And so for now, I generated the data in Python, saved it as CSV. I'm entering it into R. Ideally, I would just do all of this in R. But anyway, you can see I take the data and then I fit it into the stan package, the rstan package, and we can see how it does. First, let's take a look at these parameters, tau, alpha, beta, gamma, k, s, and sigma. And you can see that they actually line up pretty well. So the true tau, if we look over here, it was 10, and we pick it up as 9.92, alpha 0.41. Here our alpha was 0.5. The beta, true beta was 2. This estimates at 1.88, and so on and so forth. The k and the s are a little bit off, but the parameters aren't too bad. And then based on the parameters, we can see how well it did. So we get an estimated ROAS from the model of 1.23. That is very close to the 1.21 on the media input. And we can also see some other just performance metrics, such as the mean absolute error and the MAPE. So the MAPE was off by about 7%. And we can plot it over time. We can see what the average percent error was. There were some spikes. You can also see what the average absolute error was. It certainly was going up and down, but it's centered pretty close to zero. So all in all, it ended up doing pretty well when there was one media input. And we can also plot the posterior distribution. And so based on our true ROAS was right there at the 1.21. And then we can see that the posterior distribution is tightly centered and pretty close to the true ROAS. So again, I think this model did pretty good. But one of the things to keep in mind, we generated the data, right, of this form, y equals tau plus beta times this hill and add stock of the media input plus some noise. And that is exactly the structure that we put in place in the stan package as well, right? And so we are getting some help from the fact that our data generating process is using this hill function, this add stock function, and we are modeling that in the same way, so we kind of know what it is. But given the correct structure, it's still estimating the parameters very well. So now let's go back and let's add a second media input, but importantly, one that's going to be highly correlated. Now, I changed some of the values here. I changed some of the betas because I wanted there to be a little bit of a difference. And when we estimate now two media inputs, we can see that the true ROAS here, the overall is 1.15, but they have two different sort of, so media input 2 is actually quite a bit better than media input 1. Media input 1 actually has a ROAS of only 0.94, which means you're actually losing money. You actually have negative ROI on this first media spend. And the second one has a really great ROI of or ROAS of 1.35 or 35% ROI. And again, this is just data that we generated. It is the ground truth. And now we're going to see how the model does. Oh, but importantly, let's take a look at the correlations. And if you see right here, the correlation between media spend 1 and 2 is 0.899, so almost 0.9. The correlation is extremely high between these two channels. And that's actually not that crazy an assumption. Maybe 0.9 is a little high, but we often do have ad spend that trends, with the season. So we're going to spend a lot across channels during the holiday season. We're going to spend a lot, whenever we think that there is a bigger demand. So now we run this again through the stand package, but now with the two media inputs. The first thing that just really stood out when you just adding one extra media input, but one that is highly correlated, dramatically changed the runtime of this to estimate the model. So the first time through, I think it took maybe 30 or 40 minutes or so with the data. And this second time through with just one added input, no other change, took about 15 hours. I had to run it overnight. It took about 15 hours to run. But how did it do? So while the baseline tau is still pretty good, it did hit tau at being pretty close to 10. The betas are just way off for beta 2. So beta 1 got really close, 1.44 versus a 1.5, but beta 2 I had as a 2.2. You can see the real data in the Python code, and then the estimated value of 1.5. So it's actually quite a bit lower. Now, in general, because this was going so slow, I actually made it so that there was the same alpha, the same K, and the same S across both of these, and only the beta changed between the two different media spend. And now, what about the ROAS, right? So the ROAS overall is actually much lower. So the model, the marketing mix model, actually thinks your overall ROAS is negative, right? That it's actually less than 1, that you're getting negative ROI. It hits the ROAS 1 for media spend almost exactly. I mean, this 0.94 is as close to perfect as you could imagine, but ROAS 2 is just way underestimating like what the true impact is. And now this could actually have really big implications because we know the ground truth. The ground truth is that media input 2 is dramatically better than media input 1. ROAS of 1.35 versus a ROAS of 0.95. We should be, to the extent possible, shifting spend out of media spend 1 and into media 2 because it has such a bigger ROI. But the results out of the model are showing that they're actually very similar. And if you were to see this, we would probably end up pulling back a little bit on both because the overall ROAS is less than 1. And the difference between the two is so minimal that we would probably just attribute it to random noise. And if we take a look at some of these, so if you remember in the one with the model with just one result, the average error, the average absolute error, had been hovering pretty close to 0, but now you can see it's quite a bit higher. That's around like 25. The MAPE is higher as well with some spikes. And if we go down and we look at this posterior distribution, I mean, again, just ROAS 2 is just way off. Now, ROAS for 1 is great. I mean, it's pretty tightly centered right around the true one. But adding that multicollinearity, I mean, it is just not picking up the effect of 2 really at all. Now, what do you do with this, right? And so I'm going to be exploring this in some future videos. My gut instinct is that this is exactly where priors some really strong priors would help out. If we had some experimental results, say on ROA on media input spend 1 or 2, and we put that into the model and we had that as a really strong prior, I guess especially for media 2, because we do hit media 1 pretty well, ideally we would get better results. And so I'm going to be exploring that. And maybe because the runtime was so long, I might bring down some of this multicollinearity a bit. So instead of maybe a 0.9 correlation, maybe it's something a little bit lower.